all those themes are going to appear in this very applied presentation, because I really want to go for the concept. You won't see a single Greek letter here. If you think about what has happened with COVID vaccines in the last year, in the last couple of years, is really outstanding. The SARS-CoV-2 virus was identified in January of 2020. In the next few months, there was development of vaccines in the labs for the virus. And in June of 2020, not even 6 months later, the first phase 1, phase 2 trials were completed. In November of 2020, the first 3 trial results was finished and the results were announced. And in December of the same year, so we are still in 2020, in that year, the vaccine was authorized for use in many countries, and it started to be given. It was manufactured and distributed for the first recipients of the vaccine. That had never happened in history before that time. It's going from the identification of the virus to the distribution of the vaccine in less than 1 year. If you had asked me in May of 2020, I would have told you that is impossible. But it happened, and that was a very impressive effort by many people, and mostly by people in the pharmaceutical industry. So now that we have the vaccines, there are a lot of decisions that we have to make about how we use them. What is the vaccination policy? And to make those decisions, we're going to need data. We can start with data from randomized trials. This phase 3 trial that was finished in late 2020 was followed by other phase 3 trials for other vaccines. That one that I was talking about was for the Pfizer BioNTech vaccine. I'm in Germany. So but then there were many other trials a few other trials for the other vaccines. The problem with trials is that they can give us some information, but not a lot of information, because we know that the vaccine works based on the first trial, but so only for infection. But the trial doesn't say much about effectiveness for more severe outcomes, which are rare, about the benefit-risk ratio of the vaccine in different subgroups of the population. Says very little about safety too, and cannot answer questions about do we need boosters now every 6 months. So we cannot have a vaccination policy that relies only on randomized trials. That's not practical. It's not how we can do it. And in fact, it's not how it has happened. It is not practical because to answer many of these questions, we would need trials with hundreds of thousands or millions of people. If we want to know what is the effectiveness for severe outcomes, if we want to look at the benefit risk in different subgroups of our safety, and we are not going to have those trials ever. Also, it would be impractical to follow people for very long periods, the vaccinated and the unvaccinated, for example, to decide whether boosters are necessary. And it may be not even ethical to keep people unexposed to a vaccine once we know that it works. Also, the virus keeps changing. And these phase 3 trials were done mostly in a pre-alpha period. But then Alpha came, and then Delta came, and then Omicron came, and a few others in between. And we cannot do the trials every time that there is a new variant. And also, even if we could do that, we cannot do it. We cannot finish the trial in a couple of weeks, which is the time that we need to make decisions. So let me just give you an example. This is the first phase 3 trial mentioned, which was the basis for the authorization of the vaccines in several countries. This trial had 18,000 people, and it confirmed the effectiveness for confirmed COVID-19 infection. It was about 95% with a confidence interval, 95% confidence interval from 90 to 98, so very good. But for severe COVID, the confidence interval went from 20 to 100. So it wasn't that precise. We could answer questions about pregnant women, say, because there were no pregnancies in the trial. No safety signals were discovered, things that we've learned later. And it was mostly pre-alpha at the time where alpha was the dominant variant. So the trial could not answer a lot of the questions that we had. And also, even if we could do trials, it turns out that some trials apparently will never be conducted. I just told you about how impressive it was in 2020, what happened from the discovery of the virus to the distribution of the vaccines. But now go back to 2021 and 2022, and there are several vaccines available, and we're spending billions of taxpayers' money. Which of the vaccines is best? Why are we paying for some of the vaccines if they are not better than the others or safer? Do we know that? We don't know that, because those trials that compare vaccines head to head had not been done. And that's not so impressive anymore from the pharmaceutical industry. Because if you think about all the incentives, they are to develop vaccines and show that they work compared with nothing. But we are way beyond that. Now we want to know whether one vaccine manufactured by one company is better than the vaccine manufactured by the other company. That's the decision that we have to make. I'm the Minister of Health. I have to expend the next €1 billion. Where do I buy my vaccine? Which one is better? And there are no trials for that, because there are no incentives for pharmaceutical companies to do that type of trials. So we may be using vaccines that are not the best. Maybe vaccines that are causing unnecessary harm or just wasting money, because we're paying more money for one vaccine than the others and the other thing. We cannot expect that randomized trials will be available when we need them to make decisions. They can be too expensive, they cannot be ethical, they cannot be practical, or simply they are not timely. It takes a long time until they are finished. But the decisions still have to be made. We're in the middle of the pandemic. Every few months, things change, and we have to make new decisions about vaccination policy. We cannot rely on trials. We will need to use observational data that is non-experimental, data from electronic health records, from national registries, from biobanks. For non-randomized trial data is what we are going to have to use if we want to make decisions in a timely way. And that is going to be one of the main themes of this talk, which is that we all love trials, and we have been trained to believe that randomized trials are the best that we can do for causal inference. And I'm not arguing against that. I'm just saying, what if we don't have trials? What do? We still have to make the decisions. We still have to make causal inferences. And that's where observational data come into the picture. So we are going to need observational studies to guide vaccination policy, and that means we are going to need high quality data on hundreds of thousands or millions of people. And we're going to need data on vaccination, data on COVID-19 diagnosis, and data on all the adjustment variables that we may need there. And this is something that many countries have been doing. Not all, but many countries have been collecting this data in ways that can be used efficiently for the support of vaccine policies. And the idea of causal inference from observational data is simple. We know how to make causal inferences with randomized experiments, with randomized trials. The idea of causal inference from observational data is trying to emulate those trials when we don't have them. And that's what all of causal inference boils down to. Can we use the observational data to emulate a randomized trial that we don't have? If the answer is yes, then we are in business. If the answer is no, I don't think that is possible because of you are missing data on this, and this, then we cannot make it. And then there is a lot about that, about lots of methods about how to do that. But the how to do that, the that is emulating a randomized trial. That's another way of saying causal inference from observational data. And we do that because we don't have the randomized trials. We don't do this because we are in love with observational data and we think it's the best thing ever. If we could, we would be making our causal inferences from randomized trials, but we can't. So we need to use observational data. So all this discussion about whether we can or we cannot make causal inferences from observational data is kind of boring. That's not the question. The question is we have to. I mean, the issue is we have to. It's the only thing that we can do. Otherwise, we'll be making our decisions based on nothing else. So we better make our observational studies as good as possible. Always, we will have in the back of our minds a randomized trial that we would like to do. That is the target of our causal inference, the randomized trial that we would like to do. And we are using the observational data in an attempt to emulate that randomized trial, which is the target of the causal inference. So we refer to that trial as a target trial. The target trial is the hypothetical randomized trial that we would like to conduct to answer a causal question. And we can go further. We can even say that if we are analyzing observational data for causal inference, and we cannot describe the target trial, then probably we don't have a very well-defined question. So having a well-defined causal question when using observational data implies that we know what our target trial is. And this concept of a target trial has been there for many years in the theory of causal inference. The earliest time I could find the concept is in the 1950s by Dorn, who was a statistician at the National Institute of Health in the US. He didn't use the label target trial, but he was using the same concept. And then William Cochran, who was also a statistician at Harvard in the 1960s, was using the same concept of the target trial, using observational data to try to emulate a randomized trial. Don Rubin, who was Cochran's graduate student and later the chair of the Department of Biostatistics at Harvard, also developed his theory of causal inference around the idea that we need to emulate randomized experiments. And at the same time, Feinstein at Yale, or Phil Leavitt, another statistician at Cambridge in England, they were using this concept that causal inference is really about trying to emulate a target trial using. Now, all these people were talking in a very simplified setting in which the treatments that they were considering were treatments that didn't change over time, where either you are treated or you are not treated, and that's the setting in which you may have seen things like Rubin's methods, like propensity scores or things like that. There was a general theory that came with Jamie Robbins, another statistician, is biostatistician, physician, epidemiologist, also at Harvard at the School of Public Health. And Jamie Robbins in 1986 published this seminar paper of 140 pages in which he developed a theory of causal inference for observational data in the general case of time tree, which is the one that is a more general theory that we use today. This theory was later rediscovered by computer scientists like Judea Pearl. So the concept of the target trial is simple, because once we think about causal inference in these terms, then we realize that causal inference has two steps. The first one is we have to ask the causal question, and the second one is that we have to answer the causal question. And this is very important. We cannot jump into data analysis for causal inference and say, I'm going to fit a Cox model, or I'm going to do this, I'm going to use inverse probability weighting. Well, we first need to know what the question is. And to know what the question is, one very easy way to do that is to specify the target trial, specify the protocol of a target trial. Every randomized trial has a protocol that describes how the trial is going to be conducted. So we can write the protocol of a randomized trial, of our target trial, and then once we have it, then we use the data to emulate it. Or if it is possible, we can actually conduct the target trial. But if not, then we use the observational data to explicitly emulate the target trial. And what I'm saying is that if we're trying to make causal inference from observational data, the first thing that we do is to design a randomized trial. That's the beginning. The beginning is always, what is your randomized trial, your target trial? Then we use the data to try to emulate it. And when I say that we design a target trial, I mean it. I mean that we have to write the protocol of the target trial. And the protocol of any randomized trial has some components, some elements that are very, very important. One is the eligibility criteria, who is going to be part of the trial. Another one of the treatment strategies that we're going to compare, how we're going to do the assignment to those treatment strategies. It's going to be randomized, double-blind, all things. Then we have to talk about time zero, when are we going to start the follow-up and when we're going to finish the follow-up, what the outcomes of interest are, what are the causal estimates or contrast. We're going to go for the intention to treat effect or a per protocol effect, and then how are we going to analyze the data to estimate those effects. So that's in the protocol of any trial. So when we use observational data, we need to explain how we're going to emulate each of these components. Because we are going to see these are going to be the eligibility criteria, the treatment strategies, the assignment, which, by the way, when we use observational data, the assignment cannot be emulate double-blind placebo-controlled assignment. So that is never going to happen. The type of target trials we can emulate with observational data are trials that are not double-blind, because there is no blinding in the real world, and there are no and don't have a placebo control, because there is no placebo control. There is no placebo in the real world. So we actually use observational data to emulate target trials of COVID-19 vaccines, and we did it in several countries. The first study that we did, that was finished in February of 21, was the first time that the vaccine, in this case was the Pfizer vaccine, was Pfizer BioNTech vaccine, was evaluated in the real world using data from in this case it was from more than half of the population of Israel. And the first thing that we did when this study, we used data through February 1st of 2021, and it was finished a few weeks later. The first thing that we did was to specify the protocol of the target trial. So this is a summary of the protocol. We have to say, these are the people that are going to be. If we were doing a randomized trial, we will have people over the age of 16 who have not tested positive before for COVID, that have not been vaccinated before, etc. And then we would assign them to either a 2-dose course of the vaccine or to no vaccination. And if we were doing a trial, we would randomly assign them there. It wouldn't be double blind because we cannot do that with observational data. So it would be a trial in which people know whether they have been vaccinated or not. And then we would start the follow-up at the time of treatment assignment, and we'll finish at the time of one of the outcomes, or death, or loss to follow-up, or the end of our follow-up on February 1st of 2021. The outcomes that we will be looking in this trial will be not only a diagnosis of COVID, but also hospitalization from COVID, ICU, admission for COVID, and death from COVID. And we will do try to estimate a per protocol effect. This is the study that we published. In this study, we found, I'm showing you one of the graphs from the study, in which we found that the vaccine, which is the blue line here, people who were vaccinated had a lower risk of COVID diagnosis over time compared with the non-vaccinated, which is the red line. There were about 600,000 people in each arm, and we estimated the effectiveness not only for diagnosis of COVID, which was about 92%, but also for hospitalization from COVID was 87%. But now with the confidence interval from 55 to 100, we could also look at the other outcomes, and in all of them, we had, of course, a much tighter confidence interval than what the trial could find. For some of the outcomes, some of the outcomes couldn't even be studied in the trial because it had only like 18,000 people. We also could estimate effectiveness in different subgroups, and then in a follow-up of this study, we could emulate another target trial similar, but in pregnant women. And in that study, we also found that there was a much lower risk of COVID in women who were vaccinated than in women that were not vaccinated. And here, there are more than 10,000 women in each group, which is something that cannot be done as a trial. Having a trial with 20,000 pregnant women would be it's not going to happen. And we could estimate also the effectiveness for different outcomes, including for hospitalization. The natural follow-up of this is to use the same data to estimate the safety of the vaccine. And here, with more data, about 800,000 people in each arm, we could look at more than 25 types of adverse events, and we found that there was no elevated risk for most of them, although there was an excess risk of myocarditis for those vaccinated versus non-vaccinated. So it's just 1 to 5 events per 100,000 people, so it's not very high, and most people had this and spontaneously recover in a few days. But this is the type of safety analysis that couldn't be done by the phase 3 trial. In fact, we also found with this analysis that the risks that we were studying for the vaccine were actually higher if you were infected. So the risk of myocarditis was higher if you were infected than if you were vaccinated. This is without taking into account the more serious risks of ended up in the hospital or dying because of the infection. So think of everything that we could do in 3 or 4 months. We could confirm the effectiveness for serious outcomes in high-risk groups and for the alpha variant, which is what was what was the main variant during the time that the observational studies were done. And we also could look at safety. So things that we could never be able to do in that period of time with trials. Then the summer arrives and alpha disappears and delta comes. And so are the vaccines effective for delta? And again, which type of vaccine works best? We have now several. Are boosters effective? All those questions are driving vaccination policy in the whole world, and we'll have trials. So one of the things that we did now with data from the United States, from the Veterans Administration, is to estimate the risk, the comparative effectiveness of 2 different vaccines. Here I am comparing, I'm showing you the curve that compares Pfizer-BioNTech with Moderna. And as you can see, both vaccines have a low risk of infection, but the risk is lower for Moderna, both for alpha and for delta. Right. So here, this is a study based on more than 200,000 people in each group. Followed for 24 weeks. Again, something you cannot do in a trial. And there was, as you can see here, an excess number of cases per 1,000 for Pfizer-BioNTech compared with Moderna of like 1.2 cases, excess cases per 1,000 people vaccinated, and about 2 deaths per 100,000 people vaccinated. But these are only 2 of the vaccines that exist. So what about AstraZeneca? Right? So AstraZeneca, we cannot do it in Israel or the US because the vaccine was not used in those countries. So we did it in England. That's the same thing, using the national data of electronic health records in England to compare these 2 vaccines. In this case, it was Pfizer-BioNTech versus Moderna, and Pfizer-BioNTech was better. Now, boosters. Okay, so we have Delta. It looks like the effectiveness is waning. Should we give a 3rd dose? And if we do, to whom? To everyone or only to the most vulnerable? And again, there are no randomized trials. So the point I'm making here is that all these decisions will be made based on causal inference from observational studies. So the thought that we cannot make causal inferences from observational studies because they are observational, which is so in the teaching of statistics sometimes conflicts with what actually happens in the real world. So here we were using observational data from Israel, which was the first country who was using a 3rd dose during the summer to show that 3 doses were better than 2 doses. We actually showed using 1.4 million people, we found that 3 doses were better than 2 doses for not only for infection but also for hospitalization, and that was true in all age groups, not only for the older people but for the younger people. As a result of this and other studies, all countries started to recommend boosters for everybody over time, right? This is something that a randomized trial of boosters was published 2 weeks ago. So first, it's like 5 months later, which means that was done for Delta, but there is no Delta. So the trial is kind of okay, great, but it's for a variant that doesn't exist now. Also, you only had 10,000 people. So you can really look at the rare outcome as the most severe outcome. So again, what allowed us to make vaccination policy in real time was the use of observational data for causal inference. And then Omicron comes, and it is the same thing. This is one graph from a study from Spain using national registries, so that in early February you have data from December and January, and you can emulate the target trial of boosters against Omicron in real time. So next, well, we now will need to decide whether we are going to give a second booster or not. I bet that in the next 6 to 9 months, almost all of us are going to get a second booster. But when that happens, it will be based on data from observational studies again. And of course, in a while, we'll also start to see new vaccines that are designed specifically for Omicron-like variants. When those vaccines come, we will have a phase 3 trial that shows early effectiveness, and from that point on, it will all be observational studies again. So, as I told you, the target trial leads to this very simple concept, and we first have to ask the question, then we have to answer the question, and to answer the question, we need to emulate the trial using observational data. And I show you a summary of the protocol of a trial that we first emulated in February of 2021. And so let's talk briefly about how these things are done. So first, how we emulate the eligibility criteria. Well, that's simple, right? You just look for people in the data that meet the eligibility criteria that you have decided. So this is a matter of having enough detail in the data to be able to find the people that you would like to be in your trial, but it's more a data issue than a methods issue. So that's relatively simple. What about the treatment in studies? Well, again, you go to the data and have to have enough information to know who receives the vaccine and who doesn't. So if you have data, good data on vaccination, that is relatively simple too. What about the outcomes? That's also a matter of quality of the data. We need to have enough data to know who gets COVID or who gets hospitalized for COVID or death from COVID. So, but this, if we have good data, like these countries that I mentioned have, they have good data on eligibility criteria, treatment studies, essentially when people are vaccinated and how many doses and outcomes for COVID, then we can do that part of the study. But how do we deal, for example, with time zero of follow-up? Because in a truly randomized trial, we know when the follow-up starts is at the time of randomization. There is not much thinking that we have to give it, and we just start the follow-up there. But using observational data, when is time zero? When is the start of follow-up for someone? Because we could say, well, for someone who is vaccinated, start of follow-up is the time of vaccination. Fine. What about someone who is not vaccinated? When is the start of follow-up for someone who is not vaccinated? Because if I am never vaccinated, then you could start the follow-up at when the first time that I meet the eligibility criteria, some random time that I meet the eligibility criteria, or at all times when I meet the criteria. So that's what we did. To use all possible data, we use all possible times when a person meets the eligibility criteria, which is the same as saying that we emulated a sequence of target trials, not just one. And each of these target trials has the start of follow-up on a different day. So this is how this works. Let's say that we start January 1st of 2021 is the first day of the vaccination campaign. So we check whether a person is eligible or not, and if it is, we check whether the person is vaccinated that day or not. If it is vaccinated, the person goes into the vaccine group. If it is non-vaccinated, goes in the non-vaccine group. And then, among those who are not vaccinated, because being vaccinated is an exclusion criteria, among those who are not vaccinated, we look at the next day. And if they are eligible, still, we check whether they are vaccinated or they are not vaccinated. If they are non-vaccinated, they go into the non-vaccinated group. If they are vaccinated, they go into the vaccinated group. And we keep doing that day after day until the last day of the vaccination campaign before our data analysis. So if we're doing this, in the paper that I showed you before, in that project, we were doing from December 20 of 2020, which was the first day of vaccination in Israel, to February 1st, 2021, which was the last day before we finished our analysis. So that means that there are 43 days, there are 43 trials that we are estimating, one in each day, and then we pull the data from all the trials. But a person may be part of more than one trial. So a person who is vaccinated on January 15th, in the trial that starts on January 15th, is in the vaccination group. But that person may have been part of other trials as an unvaccinated person. So we are putting people in different trials so that we are using all the information that we have there. In fact, people who are always that are not vaccinated for a long time might be put in the no vaccinated group as different people in different trials. Then when we pull over all the trials, we have to keep track of how many times we are using each person, and we can use a robust variance if we want this sandwich estimator of variance, or we can just do everything by bootstrapping. But by doing this sequential emulation of target trials, we are using all the data that we have. So that is how we dealt with time zero. You can also choose just a random time for each person, and that's valid, but less efficient. Assignment. How do we emulate the assignment? Because in a truly randomized trial, assignment is randomized. But how do we do that with observational data? Because it is observational data. There is no randomized assignment. We may say that we want to emulate a trial, but it is an observational study. So we are very concerned, of course, that people who get vaccinated and people who are not vaccinated may be very different people. Maybe people vaccinated and unvaccinated are different in ways that affect their risk of COVID. For example, those who are vaccinated may have, on average, a lower risk of infection because they wear masks and because they're very careful about not getting infected. So the people who actually go and decide to get vaccinated may be the people who have the lower risk of infection anyway. So if we compare vaccinated with unvaccinated, we may find that the vaccine works even if it doesn't, just because there is compounding, because these people are different. So we need to adjust for that confounding, and that is what adjustment for confounding means. Adjustment for confounding means we are attempting to emulate the randomized assignment of a trial. So if we had information on all the confounders and we could adjust for them, there will be absolutely no difference between a randomized trial and an observational study. The difference is because we may not have all the confounders, and that's why we are concerned about causal inference from observational data. We may not have information on all the confounders, and if we are missing important confounders, we will have bias. We may be finding a lower risk of infection among the vaccinated, not because the vaccine works, but because the vaccinated are different from the vaccinated. So this is of course the main concern that we have when using observational data to emulate a target trial. And there are three challenges. We have to identify the confounders, we have to adjust for them, and then we have to try to provide evidence that whatever we are doing works. So let me talk about these three things quickly. First, we have to identify the confounders. We have to find risk factors that are not balanced between both groups. And this is something that we cannot do. Using statistical methods. Confounding is a causal concept, and to identify confounders, we need to use expert knowledge to find factors that are different between the treated and the untreated. And the reason why we cannot do this is statistically is because confounders and non-confounders behave statistically in the same way. They are indistinguishable. If you look at the data, the joint distribution, it is impossible to distinguish confounders from other variables like colliders that actually will introduce bias if we adjust for them. So the selection of confounder has to be guided by subject matter knowledge. One example of a confounder is age, because most of the vaccination campaigns in all countries have started with the older age groups. Of course, people who get vaccinated tend to be older than people who are not, so we need to adjust for age. But there are many others, like race or socioeconomic status, area of residence, prior infection, clinical characteristics. There are many things that may make a person more likely to get vaccinated and also more or less likely to get infected. So we need to measure these things and we need to adjust for them. And there are many ways to adjust for confounding. We can do this with matching. We can do this with stratification or regression. We can do this with inverse probability weighting or the G formula or G estimation. There are multiple methods that we can use to adjust for confounding, and they all work. If we have enough data, and then many times it's just a matter of personal taste, whether someone says, no, I want to do this with propensity score match, fine. While people say, I want to do it with inverse probability weighting, fine. They are all going to work if we have data on the confounders. That is the key part. It's not so much the method that we are using for the adjustment, but having the data. Unless, in some cases, we cannot use some methods because the confounders are very highly dimensional. Think of, on the case of vaccination, we need to adjust for time and place. And time, because the incidence changes from almost day to day, we need to have a very fine adjustment for time. And also by place of residence. In many cases, it has to be by neighborhood, because people have different likelihoods of vaccination and of infection depending on when they live. So because these are very high dimensional things, in our analysis, we use matching to adjust for confounding because it allows a very tight adjustment without having to make any modeling assumptions. So we did 1-to-1 matching. So say in the study in Israel, we had a 76-year-old Arab male from a specific neighborhood who received 4 influenza vaccines in the last 5 years and had 2 comorbidities. Then we matched that person with someone who looked exactly the same, but had not been vaccinated. The question now is, yes, we can use our expert knowledge. We can adjust for many potential confounders. How do we know that we're right? And that is the key question, because everything else that we're doing, we can be extremely careful in our definition of the causal question, is specification of a target trial, adjustment for confounders, all this. But at the end of the day, we don't know if we are correct, right? Because in a trial, we have physical randomization, like here. There are some things that we can do. For example, we can use negative outcome controls. These are outcomes for which the vaccine is not effective, but if they were confounding, we will find an association between vaccine and that outcome. And there is one example of this in vaccination that we can use, which is the risk of infection in the first few days after vaccination. If you remember the graph that I showed you from the randomized trial, for the phase 3 trial, there was no increased risk. There was no difference between the vaccinated and the unvaccinated in terms of risk in the first 10 or 12 days for a while, because there is still no time for the vaccine to work. Now, if there were confounded, if the vaccinated and the unvaccinated were very different, we will find that the vaccinated had a lower risk of infection even in the first 12 days after vaccination. And in fact, if we only adjust for age and sex, that is what we see. We see in the observational data that the vaccinated have a lower risk of infection from day 1. That is not possible. I mean, that is possible in the sense that there is confounding, but that is not working. So we can use this negative control to learn when we are not adjusting for enough things, because the vaccinated and the unvaccinated look different, and it is not possible that is due to the causal effect of the vaccine. So we need additional adjustment. If we adjust for everything else that we have, then we see that disappears. And if you look at the observational study there, you see how the risk curve for the vaccinated and the unvaccinated starts to separate around day 12. And in the actual in the actual trial there, it also happened. So we're finding that if the vaccinated and the unvaccinated were very different in the observational study because we are not adjusting for confounding well, we should see that the vaccinated have a lower risk in the first few days too. But the fact that we're not finding means that that we have adjusted for enough things that the vaccinated and the unvaccinated are comparable, because they only have a difference in the risk after 12 days, which is when it is supposed to happen. So we can use outcome negative controls to assess the quality of the causal inference from the observational data. We provide empirical evidence that there is not much confounding, that whatever we are finding cannot possibly be explained just by confounding. This is not a formal proof, because there is no formal proof for non-confounding. It is logically impossible. But we can bring empirical evidence that there is no confounding. So assignment is something that we can never get it completely right and be sure that it's right, but we can do something about it. Okay, so lessons from this target trial emulation. So we learned 2 things. One is that we need high quality databases. Countries who have maintained these databases and have made them available for research have been able to define vaccination policy based on their own data. The rest of the countries have made vaccination policy based on data from Israel or from the US and the UK. We also need health data experts, people who are statisticians, epidemiologists, computer scientists, informaticians, people who are there, know how to use the data and are ready to use it in a short time when the country needs that, or the states needs that. Say, hey, I have this data, I need to know. Tell me what is going on with Omicron. Should I recommend boosters to everybody based on the information that we have from people who have already been boosted? Then the most important lesson that we learn from this is that randomized trials and observational studies complement each other. Think of what happened here. First, we have a randomized trial, a phase 3 trial, that tells us that the vaccines work and they're not killing people. So based on that, we made the decision to start a vaccination campaign that generates a lot of data that we can use in real time to evaluate effectiveness and safety of the vaccines and inform future decisions about what to do. But we can do that because there was a randomized trial first that gave us a negative control. So the phase 3 trial gave us the negative control, saying there is no effect in the first 12 days, that we can use then to make sure that what we are getting from our observational studies is reasonably correct. So the trials and the observational studies are working together for causal inference. So that's why this idea that is randomized trials versus observational studies and trials are better is really everyone working together. And this means that we need to see them as not competing approaches, but complementary approaches. And many times we are going to use the observational studies while we don't have trials. And sometimes we're going to use the trials to design better observational studies. And that's exactly how the system has worked during the pandemic and has worked well. So it's important that we keep this in mind for after the pandemic. And we're not talking about vaccines, but we're talking about other effects. So emulation of target trials using observational data is what we do when we don't have a randomized trial. And even though, of course, we will always prefer trials, but we don't have them, then what we should do, what we have done, what we should keep doing is using observational analysis to guide policy in the cases that we don't have trials. And because we can expect to have trials all the time, either because it is not possible or because there are no incentives to do them, like in the case of the comparative effectiveness of 2 different types of vaccines. So the best that we can do for decision making that is evidence-based is to design our trials and our observational studies in a complementary way. And to finish there, saying that really there is no other way of doing this. And thank you very much.